What's up, stats? This is Mr. Carlson, and now we are going to be learning 6.2 t-scores. So how do they relate to z-scores? And how do they relate to the population parameters and the confidence levels and the confidence intervals that we learned during 6.1? There's one distinction and one reason, really, the reason why we're going to be using t-scores instead of what we call z-scores. And that reason is very simple. What if your population standard deviation is not known? If that's the case, then what we're going to be doing is learning t-scores instead of confidence intervals, which is a z-score. So t-scores, let's just be clear, it is a confidence level. It is a confidence interval. However, it's often what we call the studentized confidence interval because we don't know the population parameters and we kind of guess it, or we kind of assume it, or we sort of estimate it. Okay, so I'm going to skip the bell work and go straight to the confidence levels or confidence intervals for 6.1, the homework quiz. It is going to be 20 questions, I believe, and then 5 questions, or 20 minutes, 5 questions. 6.2 t-scores is going to be the next lesson. So send any partial credit requests if you desire. Okay, so 6.2 t-scores. How do I calculate the confidence intervals using what we call a one mean t-interval procedure? So I'm not going to get too far into this, but it's a very, very interesting sort of thing. It's just basically we're going to only use one mean and one mean only basically throughout the whole thing. Okay, so how do I use that, and how can I construct confidence intervals still by using t-scores? You can go ahead and click on that. That goes to Crash Course if you desire. You don't need to click on that at all. It's up to you. Okay, but like I said, you don't need to click on that. It's up to you. So in many real-life situations, the population standard deviation is simply just not known. We just don't know that. Whereas in the last slides, in the last video, we actually did know that. Like, they gave us the standard deviation, yes, of the population. So if they don't give that to us, and if we don't know it, how can you construct a confidence interval? Okay, how can you construct a confidence interval for a population mean when your standard deviation is simply not known? For a random variable that is normally distributed or approximately normally distributed, you can use what we call the t-distribution. What is the t-distribution? If the distribution of a random variable x is approximately normal, then this formula follows. So I'm going to give this formula to you. It will say t equals my sample mean minus my population mean all over my sample standard deviation divided by my n, my square root of my n, which is my sample size. So what are all these variables? Okay, so that means this equals my sample mean. Okay, and then this will equal my population mean, of course. This equals my sample standard deviation. And then my last one, of course, is just my sample size. So you do need your population mean, or at least a point estimate of your population mean. If you at least have a point estimate of your population mean, then you're good. If you have at least a population of mean from a point estimate, then you're solid. You can pretty much go through this process. But notice you're just all using samples, samples, samples. You don't know the actual sample standard deviation. So you're going to be using what we call a t-score or a t-distribution. Confidence intervals nonetheless, but a t-distribution. So critical values of t are denoted by t sub c. Here are a few properties of the t-distribution. So number one, the mean and the mode, the median, they're all the same and they are equal to 0, just like on a z-score. a standardized z-score distribution or a z-distribution. So the t-distribution is also bell-shaped and symmetrical about the mean. The total area, of course, is equal to 1. The tails in the distribution, though, are thicker than a standard normal z distribution. So they're a little bit thicker here, and that's fine. It's fine. And the reason why they're thick is because you just don't have enough information. It's kind of trying to cover up the fact that they don't have a standard deviation to kind of vary a little bit. The standard deviation of the t-distribution varies, like I said, with the sample size, but it is still greater than 1. Let's continue on these. So the t-distribution is a family of curves. It's a lot of different curves because you don't really know what it could be. So it's a family of curves, each determined by a parameter called what we call the degrees of freedom. The degrees of freedom, sometimes abbreviated DF, are the number of free choices left after a sample statistic, such as X bar, is calculated. When you use a t-distribution to estimate a population mean, that degree of freedom, those degrees of freedom are equal to the one less than the sample size. So that formula right here is simply just going to be df equals n minus 1. So that is my formula that I will be using. 1 less than the sample size. Okay? And then, of course, the degrees of freedom increase. As the degrees of freedom increase, the d-distribution approaches what we call the standard normal curve. Because as the degrees of freedom increase, that means I'm getting closer to my actual approximate normal distribution for z-scores. I no longer need to kind of estimate the standard normal deviation here. So after 30 degrees of freedom, essentially your t-distribution is going to be close to your z-score, z-distribution. So let's erase. So there's two ways technically to find your critical values, and you can use one of the following. We're not going to use the t-table just because of online learning, but you can use Desmos, okay? And so what it's going to ask you, and I'm actually going to give you all two of them here. What it's going to ask you is to find the critical value, T sub C, for 95% confidence level when the sample size is 15. Okay, so first of all, before we get there, I know my sample size is 15. So that means my second step is to use my formula df equals n minus 1. My sample size is 15. My degrees of freedom is 15 minus 1, which equals 14. So I'm going to use this number. It's not my answer, but I'm going to use this number to find my T sub C, or my critical value of specifically T sub 0.95. What is that value? Let's go to Desmos real quick to find out. So this is our Desmos calculator, obviously. Obviously, so I'm going to go over here and I'm going to scroll down. Notice I'm at 6.2 t-scores. I don't want a 99% confidence level. I want 95. And then notice how this changes, okay, just very briefly. However, the last calculator we used for 6.1, the last calculator, I didn't need to change anything. I just look and then I grab it. Here, you do need to change something, and it's this number right here. So notice if I clicked on 6.1, there's no extra number that I need to change. It's just 0, 1. That's my standard normal curve. Done. Okay? However, here, I do need to change that. That is what I call my degrees of freedom. So I need to change that to 14. Okay? I need to change that to my degrees of freedom. And so now it's 2.144. So I go over here, 2.144. And that is my degrees of freedom, or that is my critical value, my t-score, 2.144. This is my critical value. So that's how you find them. Find the critical value for 90% now when the sample size is 22. So that means my degrees of freedom is 22 minus 1. So this is 21. And so now my critical value at 0.90 equals what? So let's go over here, back again. I need to change a couple things, right? I need to change this to 90. And then I need to change this, not to 14, but to my degrees of freedom, which is 21. So 1.721. So 1.721, I go over here and I just type that in, 1.721. So that is my degrees of freedom and also my critical value. Oftentimes, Math Excel will ask you find the critical value for the right or left endpoint. If it's the left endpoint, you're just going to tag on a negative, and that's it. If it's a right endpoint, you're just going to keep it this way because of the way it's just graphed. But I doubt you'll see that, so don't worry about that too much. All right, let's erase. And let's get into some guidelines. How can I actually calculate a confidence interval even if I don't know my population standard deviation? So, constructing a confidence level interval. A confidence interval using the t-distribution instead of what we did yesterday, what we call the z-distribution, is similar to constructing what we call a confidence interval using the normal distribution. Both use a point estimate, x or x bar, and a margin of error. So it's exactly the same. It's just now we're going to be using it a little bit different. We're going to be using the sample standard deviation instead of the population standard deviation. And then I need to adjust my degrees of freedom. Literally, that's it. Everything else stays the same. But here are the guidelines. First of all, you need to verify that your standard deviation is not known. Okay, that's the very first thing. Do you actually know if the standard deviation is there? Just like the guidelines before, we needed to know that the standard deviation of the population was there. In this case, for t-scores and for t-distributions, in order to construct a confidence interval using that, I need to verify that the standard deviation of the population is not known. That the sample is also random and either the population is normally distributed or the n is greater than 30, of course. Okay, I need to find the sample statistics, n, x bar, and s. Now, s is my sample standard deviation. Now, of course, my x bar equals this formula, and very rarely will you use this formula, guys. Most often than not, they will actually give you this formula, or better yet, they'll give you the actual x bar. They'll actually give you your mean, your sample mean. So most likely you won't need to do that. But most likely they'll also give you this. But the reason why this is different is that now it's going to give you your sample standard deviation. So this is your sample and then standard deviation. Okay, sample standard deviation. I'm going to give you this formula. It's a rather nasty formula, but you don't need to calculate this by hand. This is x and then minus x bar, quantity squared all over n minus 1. Now, Desmos will calculate this for you. And even if they didn't give that to you, however, more often than not, guys, I'm telling you, they will give that to you. You don't need to find that. Okay? Identify the degrees of freedom, of course. For t-scores, I need to do that. The level of confidence and the critical value, t sub c. All stuff that we can do on Desmos. Okay? And then moving on, find the margin of error. So what is the margin of error? Well, the margin of error is very similar to the margin of error for z distributions. But now instead of using the z-score or the critical value of z, I'm going to use the critical value of t sub c, my t distribution, and then times my standard deviation of my sample all over the square root of n. So a couple changes here, but very much the exact same. Okay, very much the exact same. Okay. Oh my gosh. Okay. All right. Sorry. Find the left and right endpoints then and form the confidence interval of course, we're going to be using Desmos for the vast majority of problems. So just like before, I need to find my left endpoint. If I wanted to solve this by hand, my left endpoint would be my sample mean minus my margin of error. My second step would be finding my right endpoint. That would be my sample mean plus my margin of error. And then my third step would be to actually conduct everything and put it all together to find my confidence interval. And that would just be my left endpoint with my population mean in between, and then my right endpoint. Okay? So that right there is really the interval. And this is exactly the same as 6.1. So I see students get this confused all the time. If you don't know your population standard deviation, if you don't know, if it's unknown, that means you're going to be using t-scores or 6.2, okay? You're going to be using the t-score 6.2. If we don't know that, we have to go through degrees of freedom, and we have to use my sample standard deviation here, okay? That's all it is. All right, and so we are now going to go to our first example. These two examples I am going to solve probably by hand, and then the rest of the examples I will solve using Desmos, okay? So you randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean of the temperature is 162. So automatically I'm going to say X bar equals 162. Okay, 0.0, with a sample standard deviation of 10. So that means a sample standard deviation of 10, okay, 0.0 degrees Fahrenheit. My sea level, they tell us we want to do a 95% confidence interval. So that means my sea level is 0.95, all right, for the population mean temperature of coffee sold. Now assume that the temperatures are, of course, approximately normally distributed, which is what we need. Now, what is my degrees of freedom? My degrees of freedom, if I'm looking at 16 coffee shops, that means N will equal 16, which means my degrees of freedom is 15. So this is really and arguably my first step. My second step is to find my t-score, my z, not my z, but my t-score, my critical value of 0.95. Okay, what this will equal is 2.131. How do I find that? This will be on Desmos, and so I'm going to show you that right now. So on Desmos, I need to change my sea level to be not 0.9, but 0.95, and then I need to change my degrees of freedom here to be 15. So that will tell me my z, I keep saying z-score, but my t-score, sorry, that will tell me my t-score, my critical value there, okay? My t-score or critical value, just read it, okay? So that's how I get 2.131, right? Fantastic. So now, after I do that, I'm going to find my margin of error. My margin of error, again, I'm just going to show you how to do everything by hand, is this formula. So this is my formula. How do I do that? So I have 2.131. So I'm going to do that first. So 2.131. So 2.131 times my sample standard deviation, which is 10, all over the square root of n, which is 16. Okay. After you plug this on the calculator, you will get roughly 5.3. This is my margin of error. This is how you do everything by hand, just slowly but surely, okay? Now, to find I'm going to do step 4 over here. To find my left endpoint, I take my mean, so 162, and then minus my margin of error, 5.3. To find my fifth step, let's actually move this up here or over here. My fifth step, to find my right endpoint, I want to do 162 and then plus 5.3. So when I do that on the calculator, what I get is 156 0.7. This is my left endpoint. And when I find my right endpoint, I get 167.3. This is my right endpoint. So my last and final step in purple here would be my confidence interval. In my confidence interval, step 6, my actual interval, putting it all together, following all my steps, would be 156.7, comma, 167.3. I can be 95% confident, even though I don't know my population standard deviation. I can be 95% confident that the population mean temperature of coffee sold will be between 156 to 167. And that's pretty cool, right? And so that's how you do it, completely by hand. All right, I'm going to erase this. And let's get into the next example. Construct a 90 and 99% confidence interval for the population mean. So let's go to town on the 90% first, and then we'll go and do 99. How about that? So let's do 90%. So my 90%, my first step is going to be listing out that 0.90. I have a t score of 0.90. What is my t score will be? Let's go to Desmos to find out. So I want to change this to just be 90. So I'm going to change that 90. Nothing else changes, and I have 1.75. So nothing else will change. I'm just changing the interval. I'm changing the level, the confidence level. That's all I'm changing, the confidence level. Okay, I will get a new interval, sure. I'm changing the confidence level, which changes my t-score, my critical value. So 1.75. So that means I'm going to go over here and do 1.75. All right. So what is my new E then? My new E is 1.75 times my 10, which is my sample standard deviation, all over square root of 16, which is my sample size. This will equal, when I solve that out, 4.83. So this is my margin of error here. My fourth step to solve this, my fourth step in solving this, is going to be my left endpoint. My fifth step in solving this, actually let's move this over here. My fifth step in solving this is going to be finding my right endpoint. So my left endpoint is going to be 162 minus my new standard deviation. Sorry, my new margin of error. My new margin of error. That's going to be 157.6. And then my right endpoint, I'm going to take 162, my mean, plus my new margin of error, so 4.83. And this is going to be 166.4 when I add those up. Okay? Which means altogether my actual interval is between 157.6 and then 166.4. 166.4. Perfect. Okay. So that is briefly the 90% confidence interval. So now try to pause right now, pause it, and then do a 99. So pause it, do a 99, and see what each one is. So my C level is 0.99, and my T score, what would be my T score? Pull up the Desmos calculator and do one for 0.99. Okay? Awesome. So pause the video, see what we get. Awesome. This is what you should get. I kind of slimmed it down a little bit. I didn't really show much of the work, just really the answers. But if you got those, then you're solid and you're right on the money. Okay, try it out. If you really haven't tried it out, then I encourage you, try it out. Pull up the Desmos calculator. Try to do it yourself so that you know exactly what what you are doing. Let's erase. And now what I'm going to do is continue to do these, but I'm going to be using Desmos now. So I'm not going to be using or solving it by hand. I'm just going to solve all of them using Desmos. Okay? So you randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. The sample mean is 9.7 days. Actually, before we get this, let me split this up so that we can, yeah. Give it a second. It's thinking. Okay, so sorry about that. Let's start calculating this stuff. Okay, so let's go and see that this is n, so 36. So that's my n. So the first step that I want to do is start listing this stuff out. So first of all, I have n equals 36. Okay. The sample mean is 9.75, so that means my sample mean equals 9.75. Okay. My sample standard deviation, S, equals 2.39. My degrees of freedom would be, of course, 35. He's 1 minus, or 36 minus 1. And my C level. What is my C level? I want to construct a 99% confidence interval, so that means my C level is 0.99. Now, in this case, I don't really want to know my t-score or my critical value because it's just going to be in Desmos. I don't need that. Okay, I can find my margin of error if I want to, but I'm actually going to skip all that and bypass it because Desmos does all of it. So now let's go to Desmos and I'm going to show you. I'm at the t-score, so 6.2. I'm going to change that. I'm going to scroll down. I want to change my value here. So not 15, but I want to change it to 35. Okay? Scroll down a little bit more and I need to change these values. So what values do I need to change? Well, this is my sample standard deviation here, the S. So that means I need to change that to 2.39. I need to change my N to be 36. And then I need to change my X, my actual mean, to be 9.75. Now, when I do this, whoops, 9.75. I need to erase that, huh? When I do this, I scroll down, and this is my left and right endpoint. This is my left and right endpoint. So, what's my answers? So, my interval. My interval is between 8.67, comma 10.83. It may or may not be off by like a decimal here or there because Math Excel may want you to do like a different decimal. Like we're really precise when we're calculating this. And so it may be off by like some sort of decimal place, but that's okay. My confidence interval is 99%. That's my C level is 99%. And I can be 99% confident that the population mean number of days the car model sits on the dealership's lot is between 8.67 to 10. So roughly around on average about 9 days. I could say that. So my population mean is probably between that, and it's probably going to be around 9 days. That's going to sit on the dealership's lot. Pretty cool, right? Pretty cool. So let's start hashing these out. Let's get to my next example. Let's erase all this junk. Let's get to my next example and do 90. So everything else stays the same. That's the cool part. So everything else will stay the same. All I need to change now is 90. Okay, the 90. That's all I need to change. Ready? So now what I do is go over here. I just go up and change this 99 to a 90. Again, everything stays the same. I now want to construct a 90% confidence interval for the population mean number of days for the car model that sits on the dealership's lot. And I just want to compare the widths and just see what it is. So for 90, I scroll down, what's my confidence interval? So for my interval for 90%, my interval is 9.08, comma, 10.42. Okay, that is my first answer for 90%. Now this was a little bit thinner. Okay, it's a little bit thinner because it's not as restrictive. So 99% confidence interval is going to be like pretty restrictive, right? So if you're looking for a C level of 99%, it's probably going to be a bigger margin of error. But since I kind of slimmed down and decreased my C level to be 90% instead of 99, my margin of error is going to be a little bit decreased. So it's not going to be as slim. So this is actually a little tighter interval here. Okay. Now let's do 95. So I'm going to do the exact same thing. Just go over here. I'm going to change not 90. I'm going to change from 90 to 95. So I don't want 90. I want 95. So I scroll down. Everything else stays the same. And then what is my intervals? So I scroll down here, and that's my left and right endpoints. So I have 8.9. 4 to 10.56. Okay, what does this mean? That means compared to 90, since it's a little bit more restrictive, the C level of 99% is a little bit more restrictive than 99 or 90. It's going to be a little bit fatter. So my confidence interval, because it has a C level of 95%, is going to be a little bit fatter, which means my margin of error here is a little bit fatter than 90 degrees. But it's still thinner. 95% is still thinner than 99. Does that sort of make sense? All right. Let's erase this. And let's move on to a couple more examples here, and then we'll almost be done. The grade point averages GPA for 12 randomly selected college students are shown at the right, and I'm actually going to just show them down here. So shown below. Assume that the population is normally distributed, so that's good. That's great. The sample mean, sample standard deviation, and then we want to find the sample mean and the sample standard deviation. So that's intense. And then construct a 90% confidence interval for the population mean. So when I have something like this is really interesting because they're actually telling us to find the mean and the standard deviation, which kind of blows, to be honest with you. Okay, and so let's start off with just naming our C level. Our C level, they want a 90%, so we're going to do a 90%, okay, which is 0.90. Other things I need to know, my N. What's my N? It's going to be 12. Okay, so it's going to be 12. My degrees of freedom then is 11. And then what is my X bar? And then what is my S, my sample standard deviation? This is something that we actually need to plug in using Desmos. Okay, so I'm actually going to go and close this real quick. I'm going to go over here. And let's just label this, let's just label this A. Okay, so a list. I want to make a list. So 2.3, comma 3.3, comma 2.9, comma 1.7, comma 0.6, and I'm just going to continue this train. I should get 12 altogether, and that's what I do get. I do have. Now to find my mean, all I have to do is just type in mean and then of A, and that is my mean. So I go over here and I just type or write in 2.375. That's my mean. All right. Now to find my standard deviation, all I need to do is type in STDEV and then of A. And that is my standard deviation of my sample. So I just write in 1.144. So those are the two things I need to find. And now I can use all of that information. I can use all of that information and go back up and actually write in all my sample size, my sea level, my degrees of freedom, and then I can find my interval. What is my 90% confidence interval here? Okay, so let's do that. I'm going to erase this because I no longer need that stuff. And then I can go down here. I want not a 95, but a 90. And then my degrees of freedom need to change. Do not forget your degrees of freedom here. It's different than the Z distribution, the 6.1 confidence intervals. My sample standard deviation, we got 1.144. And then for my N, we got 12. For my sample mean, I got, let's erase this, I got 2.375. And now for the big reveal, I have this as my confidence interval. So my confidence interval is 1.78, comma, and then 2.97. So that means you can be 90% confident that the average from this group of 12 randomly selected students, the population average is around 1.78 to 2.97. That's a pretty low GPA. I mean, I'm not gonna lie. If you have that GPA, you should not have that GPA. You should get on that. All right. Awesome. So that is basically the T scores. I have a couple more things to go over, and then we're pretty much done. A couple more things, just last minute things. I don't really need decimals anymore here. So just a couple more things, and then we are essentially almost done. It's loading again. Fantastic. So the flow chart right here will describe when to use the standard normal distribution, so the z-score, the 6.1, and when to use the t distribution, okay, the 6.2. So 6.1 is your z-scores or your standardized normal distribution, and then your t distribution is 6.2 when they construct for a confidence interval or for a population mean. So if n is greater than 30, you're going to ask, is n greater than 30? If you say yes, then you're going to use the normal distribution with this formula. Okay? If your population standard deviation is unknown, then you're going to use S instead of this. So you're going to use S instead of that. And then you'll use 6.2. Okay? Sweet. If you say no, n is not greater than 30, okay, then you're going to ask, is the population normally or approximately normally distributed? If you say no, you cannot use the normal or the t distribution, okay, because then it doesn't follow from the central limit theorem. You can't approximate anything, so you can't do it, okay? You can't even find a confidence interval at all. So Is n greater than 30? You say no, but is it approximately normally distributed? Yes. Is the population standard deviation known? If you say yes, then you're going to be using this formula, and that's from 6.1. If you say no, you're going to be using the t-score formula with n minus 1 of degrees of freedom, and this is 6.2. Okay? So I hope that kind of summarizes things of when you use which one. And it's very, very important when you use which one, because Math Excel is not always going to distinguish between the two. So let's kind of try this out. Standardize, or what we call studentize. So 6.1 for standardize, or 6.2 for studentize. You randomly select 25 newly constructed houses. So automatically, it's not greater than 30. So that's kind of concerning, but let's continue on and read, and let's find out. So the sample mean is 181,000, and the population standard deviation is this. So automatically we have the population standard deviation, so that's amazing. So that means I'm going to ask, is the population standard deviation known? And we say yes, it is. Okay, it is definitely known. Okay. Now, assuming construction costs are normally distributed. So now, normally distributed, that's what I'm going to say. Normally distributed, is it normally distributed, or is n greater than or equal to 30? Well, it's definitely not greater than or equal to 30 because my sample size is 25, but it is normally distributed. Because these two things are in place, my decision is to use my standard, okay, my standardized graph, which means I'm going to be using 6.1, okay, and not 6.2. So this is a 6.1 scenario. I'm not going to be using the t-distribution. I'm going to be using the standard normal distribution with z-scores 6.1, okay? So let's try another one. And this will be our last example. So you randomly select 18 adult males. Automatically, we don't have n greater than 30. And measure the resting heart rate of each. The sample mean. So I have a sample mean. Oh, that sucks. So that means automatically, do I even know the population standard deviation? I don't know. I have a sample mean, and that's not necessarily good. And I continue reading, and I do read that I don't have that. I don't have the population standard deviation. I only have the sample standard deviation, which means I don't have this. Okay, so now let's ask our second question. Is it normally distributed, or is n greater than or equal to 30? Okay, which one? Well, n is definitely not greater than or equal to 30, so hopefully it's normally distributed. Assuming that the heart rates are normally distributed, awesome. So that is true, okay? But the problem is, do we really know the standard deviation? So it doesn't really matter if it's normally distributed or not. Although, if it wasn't normally distributed, we couldn't do anything. But since it is, we can at least do something. We can at least do 6.1 or 6.2. But then, now that we know that the population standard deviation is not known, we can't use 6.1. We have to use 6.2 t-scores. Okay, we have to use the t-scores, or what we call the studentized version of confidence intervals. Okay, I hope that makes a little bit more sense, kind of wrapping up everything together and which distribution we would be using. All right, so what did we learn? We learned how to interpret the t-distribution and the t-distribution table, and basically how to compare between the t-distribution and the z-distribution. We constructed and learned how to construct and interpret confidence intervals for a population mean when my sigma, my population standard deviation, was not known. So be sure to be working not on your project, so we're not doing a project, but be sure to be working on your homework at least. Okay? Until next time, this is C Squared Mathematics. Make good choices.